Hello guys and welcome to my channel. So today we are going to be learning control systems theory, and precisely we are going to be learning about stability criterion. Now the stability criterion we're going to be considering today is Routh's stability criterion. So if you're not too busy, grab your pencil and your paper because you're going to learn a lot. And after I give you a brief refresher or a brief background into the Routh stability criterion, we are going to solve two problems, probably two assignment questions, and you will learn how to analyze any further problem that may arise. So let's dive in, and I believe you're going to understand. Now, let's refresh ourselves on what is the Routh stability criterion. What is it about? First of all, the Routh stability criterion is well known as Routh-Hurwiths stability criterion. Okay, Routh-Hurwiths stability criterion. So you might be wondering, where is Hurwitz coming from? Actually, it's actually together, like somebody building on the work of someone. So as you can see, Routh did his work in 1905 and Hurwitz did his own work a lot more earlier in 1875, and both of these geniuses, their work gives a method of indicating the presence and the number of unstable roots, but not their value. Now, what does this mean? Now, anytime we are dealing with control system, it is very important that we build the control system to be stable. Now, when we are designing our control system, we have what we call the characteristic equation of that control system, and that characteristic equation can yield roots like any other equation. Okay, it's a polynomial or characteristic polynomial. It can give us different roots. Now we want to make sure that the interpretation that we get from the roots of those characteristic equation all the time will plunge our system always into stability. Okay, so with the Routh and the Hurwitz stability criterion, it helps us to indicate from our characteristic equation whether we might have unstable roots or not, but it does not determine the value of this characteristic root. It just helps us to indicate the presence of unstable roots and perhaps the number of unstable roots. Okay, so anytime you're designing a control system, if you want to know the number of unstable roots in that control system, okay, or if you want to determine if your control system will have unstable roots, okay, then you have to use the Routh-Hurwitz stability criterion, or Routh's criterion for short. So I hope it's getting interesting. I hope it's not getting really boring, but let's dive in. So we are getting there. So first of all, let's see a general characteristic equation of n degree, represented by this long equation over here. So we have an s to the power of n. An is just like a coefficient, and an minus 1 is the coefficient to the term in the lower degree than Sn, and it keeps going till we meet our constant term over here and equal to 0. So these are characteristic equations. So what is the Routh-Hurwitz stability criterion? How can we use this criterion to indicate the presence of what? Unstable roots, and perhaps to know the number of unstable roots. So if we are given any characteristic polynomial or characteristic equation, the first thing is that for there to be no roots with positive real parts. Okay, so anytime you see this in control system, a root with a positive real part. For instance, you might solve an equation and you get s to be minus 2 plus or minus j5, or you might get s to be 3 plus or minus j2, for instance. Okay, j is the imaginary number. Now, when we have a positive real part after solving for the root of any characteristic equation, when we have a positive real part, it indicates instability. Okay, I'm sorry about that, instability. So a positive real part or a positive root, we could get our root to be -2, -3, or let me say 5. Whenever we have negative roots or negative real parts, okay, it indicates stability in control system. But anytime we have a positive root, okay, let me say like a 5 or a positive real part, after solving for the roots of the characteristic equation, it indicates instability. Okay, so sometimes we don't want to actually solve for that characteristic equation, but we just want to test if at all there will exist maybe positive real parts. So we are always interested in the presence of instabilities in our control system. That's why we are actually after the positive real parts, because if we have negative real parts, then we are safe. Okay, negative real parts or negative roots, we are safe. But whenever we have a positive root from our characteristic equation, then we actually need to actually deal with it, because it may affect the performance of your system. Your system will be unstable. Okay, so if for there to be no root with positive real parts, then there is a necessary but not sufficient condition that all the coefficients in the characteristic equation have the same sign and none are zero. What does this first point mean? It means that if I have my characteristic equation like this, and I want to be sure that I'm not going to get a positive root, okay, I'm not going to get a positive root or a root having a positive real part, then the first criteria is that all the coefficients in this characteristic equation, they must have the same sign. Whether it's plus or whether it's minus, all of them must have the same sign, and none of them should be zero. That means no term should be missing. In a characteristic equation of order n, I should have all terms complete in that characteristic equation. So if I have the characteristic equation of order 3, I must have my s cubed term, I must have my s squared term, I must have my s term, and I must have my constant term. So no term should be missing. So if all the signs, okay, are the same and no coefficient is missing, that means if this first criteria is satisfied, okay, then the necessary and sufficient condition for stability is either, okay, so why is it that, why do we normally refer to things like this in mathematics? Okay, there is a necessary but not sufficient condition. Now the first condition is just it's just like, it's, how will I put it, it's just like let me say your first door to success. Okay, is your first door to success. Is a necessary condition, but is not sufficient enough. You still need to open more doors so that you can achieve the aim of your test. Remember, you want to know the presence of what instabilities, and you want to also determine the number of instabilities. So that's about the Routh-Hurwiths or the roots criterion. Now the first condition, which is necessary but not sufficient, is that first of all coefficients must have the same sign and no coefficient should be missing. Now if your characteristic equation satisfies option A above, then you now have to go to either B or C. Now let's see what is in B. Now in B, then all the Hurwitz determinant of the characteristic polynomial must be positive, or alternatively, pointing us to C, all the coefficients of the first column of the roots array should have the same sign, and the number of sign changes indicates the number of unstable roots. Okay, so this might be looking a little bit too cumbersome for you, but I just want you to be strong, because we're going to dive into example. I'm going to explain everything in such a way that you understand, even though you don't have like any prior background on this subject up to this point in time. Now what we are trying to say is, if we have satisfied the first condition, that means all coefficients should have the same sign, and secondly, no coefficient should be missing, then we can either decide to use option B or to use option C. Now for the purpose of this course, of today's lesson, we are going to use option C, because we want to throw more emphasis on the roots criterion, that's the roots array. So option C is telling us that all the coefficients in the first column of the root array should have the same sign. Now I'm going to show you what this means. Okay, now the number of sign changes indicates the number of unstable roots. So for there to be no instabilities in our system, then all the coefficients in the first column of the root array, we are going to see the root array shortly, all of them must have the same sign. But if peradventure you solve for your root array and you discover that the first column has different sign, then the number of sign changes will tell you the number of unstable roots. Okay, so we are going to look at the root array. So let's look at the root array. This is how the root array looks like. So when you're given any characteristic equation of this form, like we established earlier, this is how you're going to present your root array. So you're going to present your root array. We'll start from here. That's the highest degree, s to the n, then s to the n minus 1, s to the n minus 2, s to the n minus 3, and we'll keep going until we get to s to the 0. S to the 0 is the coefficient, is the algebraic variable that is attached to the constant term. That's a naught. As you can see, here is s to the 1, here will be s raised to the power of 0. S raised to the power of 0 is 1. Is that okay? So when you draft out your variable, that's your s variable in this particular form, okay, from your characteristic equation, then you now start filling the coefficient. So this is how I'll take it. I'll take this an and I'll place it here. Then I'll now jump one term. I'll take this one and I'll place it here. Okay, I think I missed something. Here is n minus 2, and you have s minus 3, I think, here, like that. So very good. Here is supposed to be an n minus 2. You have an s n, then you now have an minus 1 sn minus 1, then an minus 2 sn minus 2. Okay, sorry for that. This is how it's supposed to be. Okay, so this is our characteristic equation. I'm sorry about that little error over there. So what you do is, as you can see, you take this first term and you place it here, and you jump this one, then you take this one and you place it here. You jump again, you jump by one and you place it here. Okay, so you keep going like that. So after you finish that, when you now come to this column, you're now going to take this term. Okay, that's the one here. You place it here, then you now jump one. When you place it, you can see when you jump one, it's going to land at n minus 3. So you keep jumping like that until you get there. So usually when you first draft out your root array, you only have these two columns at these two rows at first. So the next thing is now for you to figure out how to get B1, B2, B3, C1, C2, C3. So I'm going to show you how to get B1, B2, B3, and C1, C2, C3. So to get B1, okay, B1 is going to be 1 divided by an minus 1. And you now solve these determinants. The determinants will comprise of this term here and this term here. Okay, so you have an minus 1, an, and you now have an minus 3 and an minus 2, like this. So this is for our B1. Is that okay? So let's check out our B2. So to get our B2, we'll have the same pattern. B2 will still be solved with respect to this term over here. So you have 1 all over an minus 1. Then you now have the determinant is going to comprise of this one again. That's an minus 1 and an. But this time around, instead of using this column here, we're going to use this one here, an minus 5 and an minus 4. So if there are more terms, okay, like if you want to solve for B3 now, can you guess what B3 will be? If you're good with understanding pattern, you will see that B3 will also be 1 over an minus 1. Then if you want to get the determinant of B3, then you now have an minus 1, you have an. Then instead of you to have an minus 5, you probably have an an minus 7 and an an minus 6, and so on and so forth. So that's how it keeps going, and so on and so forth. So the pattern keeps increasing in that way. So assuming you want to find your C1, okay, your C1, that's this one here, this one here, and this one. So let's find C1, C2, and C3. So just like B1 depended on this particular term over here, C1 is going to depend on this B1 like this. So C1 will be 1 all over, you have your B1. Then you now find the determinant between what, this term over here, this collection over here, this array. So you have B1, B2, you have an minus 1 and an minus 3. Is that okay? So that is going to be for your C1. So for your C2, then you will still have 1 over B1. Then who can guess what it will be? Definitely we'll have a B1 and an an minus 1 here. This row, this column, sorry, always stays the same. Then to get your other column, instead of you to use this one, that's this and this, because you've already used it, you come to this place and this place and pick what is there. So I'll have B3 and an minus 5 somewhat. Okay, so you can use the same pattern to figure out what C3 is going to be. Definitely, perhaps if you have a D, for instance, let's say you have a D1, let me just forge something like a D1, Sn minus 5, I'll have D1, D2, maybe I might have D3, I don't know. So if you want to find your D1, you just follow the same pattern. So D1 is going to depend on what, C1 over here like this. So to get D1, you're going to say D1 is 1 all over C1. Then you now open, of course you already know that you capture this for 1, 2, 3, 4. Is that okay? C1, C2, B1 and B2. So you have C1, C2, B1 and B2. So if perhaps you want to find B2, then you know it will be 1 all over C1. Then this column will still be C1 and B1. Then instead of it to have C2 and B2 here, you will have what, C3 and what, B3. Is that okay? So that means for D2 you use this one and this one and this one and this one. So it keeps going like that, it keeps going like that, it keeps going until you find all the coefficients. So what exactly do we want to do with these coefficients? Now I want you to take note of something on the roots table. When we finish solving the roots table, this term and this term will be the only ones existing on the last two terms. That's on the S term and on the S to the 0 term. We'll just have only one terms. So I just represented them with P1 and Q1. You could use any constant you want, but just know that for the last two terms we'll just have only one value. We will not have as much as this one. So these numbers could be variable. It depends on the power of n, or sorry, it depends on the value of n. So you could have a long or a lengthy array or a short array depending on the power of n. So we are going to see it, but just know that for these last two terms we'll have only one value situated here. Now our area of interest is this particular first column over here. Our area of interest is this first column. So let's refresh ourselves on the criterion again. For Routh's criterion, it says that all the coefficients of the first column should have the same sign. Okay, they should have the same sign. Then if peradventure there is a sign change, and the number of sign change will tell me the number of unstable roots. So for my system to be stable, for my system not to have any positive roots or unstable roots, I have to make sure that all these coefficients that I have gotten on this first column, all of them have the same sign. So that's just the emphasis of the roots criterion method, that all the coefficients on the first column of our roots array should have the same sign. Is that okay? They should have the same sign. Now, if you have gotten everything that I've explained from the first minute of this video up to this point, then we are ready to delve into the assignment solutions, and I'm going to show you how we are going to apply everything we've learned to getting our assignment solutions correctly. Okay, so I'm gonna write a question right now, and we're going to dive into that. Okay guys, here we are at assignment solution for the first problem, and the first problem is that we should consider the characteristic equation x to the 4 plus 2x cubed plus all 4 plus k in x squared, then plus 9s, then plus 25 equal to 0. So we have to use the root stability criterion to determine the range of k for stability. So this is how we are going to go about this problem. So the first thing that we're going to do is, given I didn't spell it very well, so given s4 plus 2s cubed and plus 4 plus k s squared and plus 9s plus 25 equal to 0. So we build our roots array as follows. So we are going to form the roots array for this particular characteristic equation. So this is how it's going to be. I'll form my roots array like this. So first of all, I'll start with the highest power, which is s4, and I'll now go to s cubed, then I'll now go to s squared, and I'll now go to s, which is the same thing as s raised to the power of 1. Then for the constants, I can see an s to the 0. S to the 0 is 1, remember. So this is descending powers, okay, of my s values. Now, how will I form the first two rows of my root array? So the coefficient of s in s to the 4 is 1. Okay, so remember, according to what we had over here, it's about jumping. Okay, when you collect the first term, you now jump by 1 and collect the next term. You now jump by 1 again and collect, and you keep going like that. So for the second row, you collect the second term here, and you now jump by 1, you collect. So it's all about like jumping your steps each time you move. So this is how I am interpreting it in my own way. So this is my characteristic equation. So I'll select this one, I'll jump, I'll now select this one. So I'll have 4 plus k. Okay, then I'll now jump again and select the last one, which is 25. So we keep jumping by 1 and we select the coefficients. Okay, so I would have jumped again, but it's just that the coefficients are exhausted at this point, so there is no need to jump any further. So to get the one for s cubed, I'll now start with this one, which is 2. Is that okay? So we'll now jump by 1 and we'll go to 9. And since there's nothing to jump by again, you can actually leave here blank, or you can pad it with a 0. Okay, you can pad it with a 0. So this is how we are going to find our coefficients here. So I'm just going to use something like a green ink. We need to find our b1 and our b2, then if possible b3 maybe or not. And remember, for the last two terms we just need only one. So I need my c1 and I need my d1. So I want to find my b1, I want to find b2, if possible b3, I want to find my c1 and my d1. So let's go on to see how we are going to find that. Now, to get b1, b1 is going to be what? You have to what? Remember that it depends on this value over here, okay, from the formula. So I'll have 1 all over 2. I'll take the reciprocal of this value, and at the same time I'll now find the determinants. 2, 1, then 9, and what? 4 plus k. 4 plus k. So let's find and see what we'll get. So this will be 1 all over 2, then I'll have 2 times 4 plus k, 4 plus k, and minus 1 times 9 is 9. So when I solve, I'm going to have is 1 over 2. I'll have 2 times 4 is 8 plus 2k minus 9, and if we arrange it, we're going to have 2k minus 1 all over 2, and someone can leave this as k minus 1 over 2 or k minus 0.5. So this is our b1. Okay, so our b1 is k minus 1 over 2, so I'm going to put it here, k minus 1 all over 2. Is that okay? So let's go ahead and find our b2. Our b2 will still depend on this value over here. So to get your b2, you will have 1 all over 2, and you now have, to get the matrix, it will still be these first two values. So you have 2, 1, then the other part of your matrix leading to the determinant will be what? These values over here. You can see that 0 that I padded is useful. I now have 0 and 25. I'm not going to use this and this because I used this one to find b1. So I'll jump to this two. That's 0 and 25. 0 and 25. So when we solve it, what we're going to get is, we're going to get 2 times 25, which is a 50, minus 1 times 0 is 0, and all of this is multiplied by 1 over 2. So at the end of the day, you discover that we'll have 25 at the end of the day for b2. So we've gotten our b2. So b2 is 25. So if you want to solve for b3, although it's not necessary, let me just show you that it's not necessary. So b3 will be 1 all over 2 again, 1 over 2. That's still the same value over here. And to get b3, you still use this first 2. That's 2 and 1. You have 2 and 1. Then b3 needs to get another value here, and we can't use this one. We can't use this one because they've already been used. So it's just like imagining there's a 0 and 0 somewhere here. So 0 and 0, nothing. So if you expand this, you get 1 over 2 times 0 minus 0, which is still the same thing as 0. So b3 is 0. It's as good as it doesn't exist. So the only two values I have is my b2, which is 25, and my b1, which is what? K minus 1 over 2. So I've gotten this one and this one, and I'm good to go. So I need to go and find what? C1. So to find C1, remember C1 would depend on this value over here. So this is how we find C1. So our C1 is now going to be 1 all over K minus 1 over 2, and we'll now find our determinants. So our determinants will now comprise of what? K minus 1 over 2, 2, 25, and 9. Very good. So you have K minus 1 over 2, and you have 2, you have 25, you now have 9. So I hope I got that correctly. So yes, perfect. So if we expand, we'll have 1 divided by K minus 1 over 2, then into this times this is going to be 9 into K minus 1 over 2, then minus this times this is going to give you what? 50. Is that okay? So if you have it like this, the next thing you're going to do is you have 1 all over K minus 1 over 2. So let's just simplify. We'll have 9 into K minus 1 over 2, then minus 50. Oh, I repeated my steps. So the reason why I did it like this is for you to see that this is still the same thing as 9 into K minus 1 over 2 minus 50, everything divided by K minus 1 over 2. So if you solve, you get C1 as this cancels this is still 9 and minus 50 over k minus 1 over 2. So we can leave our C1 on this form. Is that okay? So we can leave our same one in this form. So I hope it is understandable. So I'll leave my C1 as 9 minus 50 divided by k minus what? 1 over 2. Okay, 9 minus 50 divided by k minus 1 over 2. That is my C1. Now remember, I told us that when we get to the last two terms, that's my s to the 1 and s to the 0, you don't need to find C2 because you just need only C1 and your D1. Is that okay? So I will from this point proceed to find the value of D1. So let's go and find the value of D1 and see what D1 is going to give us. All right, so to find D1, of course, very good, it will depend on this value over here. D1 will depend on this particular value over here. So this is D1 is going to be 1 all over, you have your 9 minus 50 all over k minus half and into, okay, so to get the matrix for D1, it will be this value and this one, and I can't see any value here, so I can just pad it 0. So 0, 25, this and this. So what I have, if I can remember, is 9 minus 50 all over k minus half, and I still have my k minus half, and I have 0 and I have 25. So to find D1, D1 is now going to be what? If you solve this matrix very carefully, very carefully, this is what you observe. You get a 1 divided by 9 minus 50 all over k minus half into this times this is just going to be 25 multiplied by 9 minus 50 all over k minus 1 over 2. Is that okay? So this is what will result, because this times this is 0, so this value minus 0 is just this value. So as you can see, this one can cancel out. At the end of the day, your D1 will just be what? 25. Is that okay? So D1 is 25. So the value that you get at this point, if you observe, if you solve many questions, you discover that the value you get at this point will always correspond to the constant term of your equation. So if you solved your work correctly, anytime you do Routh table, you should know that the value you get here at this last point will almost resemble, or it should be equal to, your constant term. Okay. Now we have gotten all the values on the first column. So these are first column, our second column, our third column. Okay, so according to Routh's criterion, Routh wants us to make sure that all the values that appear on this first column must have the same sign. Now, if we observe carefully from this one is a positive value, this one is a positive value. Okay, so whenever something is positive, okay, when something is positive, okay, that means it is greater than 0. I hope that's true. So 1 is positive, 2 is positive, 25 is positive. So the only problem that I have is that I have k minus 1 over 2, and I have 9 minus what? 50 all over k minus 1 over 2, and I don't know whether they will be positive or not, but I can actually constrain them and make them positive. And the acts of you constraining these unknown terms over here to make them positive, or to make them have the same signs with what you have, is what will now give you the required range of values so that your system will be stable. Now this is what I mean. So okay, I can now comment, put a little comment and say all terms on the first column, sorry about that, first column seem to be positive. okay, except, so let's write it what we have k minus 1 over 2, then 9 minus 50 divided by k minus 1 over 2. So except k minus 1 over 2, and we have 9 minus 50 into k minus 1 over 2. So this is how we now conclude. So for our system to be stable, then this value has to be positive. In other words, k minus 1 over 2 has to be what? Greater than 0. Okay, so this is equation 1, and at the same time 9 minus 50 all over what? K minus 1 over 2 has to be 0. That's equation 2. Is that okay? So you will now solve these two inequalities, and from the answer that you get, you've now gotten the range of values that will keep your system stable. That's the range of value of k that will keep your system stable. So from equation 1, you have your k is simply what? Greater than 1 over 2 when you take 1 over 2 to the other side. So you keep this one somewhere. So from equation 1, then we'll now go ahead and solve equation 2. So solving equation 2, we're going to have, of course, 9 minus 50 all over k minus 1 over 2 should also be greater than 0. So if we solve it in this way, what are we gonna get? If we solve it in this way, first of all, I'll say 9 is greater than 50 all over k minus 1 over 2. Is that okay? So if we exchange the position of this term and this term, you have k minus 1 over 2 is greater than 50 all over 9. So if you solve, you now get finally k is greater than 50 all over 9, then plus 1 over 2, and this evaluates to 100 plus 9 all over 18, which is 109 divided by 18. So our k is greater than 109 over 18, and k is greater than 2. So in mathematics, when you solve two problems, okay, you solve two inequalities for one particular variable, and you discover that you have the inequalities pointing in the same direction, so you're going to look for the one that is more towards the right or more towards the left. So I call it more positive or more negative. Now in the first case, I got k is greater than what? 1 over 2. In the second case, I have k is greater than 108 divided by 19. We can actually evaluate 108 divided by 19 and see what it gives us. One 8 over 18, I'm sorry, and that gives us a 6.056 approximately. So you have in this place k is greater than 0.5 on one hand, and k is greater than 6.056. So we are going to use the one that is more greater in this case. Okay, so for our system to be stable, the value of our k must be what? Greater than eventually 0.5 and what? 6.056, which means I'll choose this one since this one is more positive than this one. So the range of my system stability, okay, is going to be 6.056. So range of stability is going to be 6.056 to infinity. Is that okay? Like this. So this is going to be the range of stability, or you can say k is such that we have 6.056 is less than k and less than infinity. So any value of k that you pick from this particular range 6.056 up to infinity will ensure that our system described by this characteristic equation over here is going to be stable, okay, all the time. So this is for this problem, and some of you might be wondering what this k means. K means gain. Sometimes we call it open loop gain, okay, open loop gain. So it's actually called the gain of your system. It's a very important parameter in control system. So it can actually have values ranging from 0 to infinity. So you should make sure that for this control system, if you want it to be stable, and our values of k should be at least from 6 down to about infinity, thereabout. So that will provide a good range for our system to be stable. So what happens when you pick any value other than this range, outside of this range, and you discover that your system will begin to have unstable roots or positive for instance, positive real parts when you solve your characteristic equation by choosing a value of k outside of that range that we specified, your characteristic equation will end up having a positive real part as part of its roots. It will have 4 roots, and one of those roots will have a positive real part, or more will have positive real parts, and that will drive your system into instability. So this is about the first problem. So we're going to look at the solution to the second problem and see how it goes. Is that okay? All right. Okay guys, here is assignment problem 2, and they want us to consider the closed loop system, and with this closed loop system we want us to determine the range of k for stability, and assuming that the value of k is greater than 0. Okay, so this one is quite a little different, but the first thing we need to determine what the characteristic equation. So that's the first thing we'll do. So determine the characteristics equation. So this is how we are going to determine the characteristic equation. So anytime you're given a closed loop system in this form, closed loop system are usually given like this: your g of s, then you now have something like a feedback, then sometimes in this place there's something we call a h of s. Okay, h of s. So this is how it looks like going in this direction. So anytime you're given a closed loop system like this, so there's supposed to be an arrow here. So if you're given a closed loop system like this, then your closed loop system can still translate to this form if you are very conversant with reduction, okay, of block diagrams. This will be 1 plus g h of s. Okay, that's the product of these two, so it's still equivalent to this. Now this is our characteristic equation. Our characteristic equation is this guy over here. When you carry this expression and you equate it to 0, you get your characteristic equation. Now for this closed loop system, funny enough, there is no h of s, but anytime you don't see any h of s here, it means that your h of s, that's your feedback gain, is 1. Okay, h of s is our feedback gain. Okay, it's 1 in this case. So what we are just going to have is that in forming our characteristic equation, our characteristic equation is 1 plus g, okay, of s, you can call it times h of s, okay, equal to 0. So where our h of s is equal to 1 and where our g of s is equal to, if you want to get your g of s, you can see in this box g of s is standing alone, but in this particular expression we are given, I have two boxes. Well, you can cascade them together and you're going to have only one box. Okay, when you cascade these two together, it means you're multiplying this by this. Is that okay? So when you multiply it, your g of s is now going to be k into what? S minus 2 all over s plus 1, then you now have s squared plus 6s plus 25. So this is your g of s. Is that okay? So this is our g of s, that's the product of this and this, and our h of s. So now that we have g of s and h of s, we can now what? Interpret our characteristic equation as follows. Or our characteristic equation is, we have 1 plus g of s times h of s, which is k into s minus 2, then divided by s plus 1, and you now have s squared plus 6s plus 25. Is that okay? So equal to 0. So when we solve this, we are going to get s plus 1, s squared plus 6s plus 25, then plus k into s minus 2 gives 0. So this is what we're going to get. So let's expand the brackets gradually. So s times this is going to give me s cubed, then 1 times s squared is s squared, then plus s times 6s is going to give you 6x squared, then 6x times 1 is going to give you 6s, then s times 25 is going to give you 25s, then plus 25 times 1 is going to give you 25, and you now have plus k times s is ks, and you now have minus 2k equal to 0. So we're going to collect the like terms. I'll have s cubed, then plus this and this will give you a 7s squared, okay, then plus this and this is going to give you a 31s. Then if you collect this term together with it, you're going to have ks, then you now have plus 25, then minus 2k equal to 0. I hope we're together. So at the end of the day, we have s cubed plus 7s squared and plus 31 plus k s, then plus 25 minus 2k equal to 0. So this is our characteristic equation over here. So having gotten our characteristic equation, we are now going to form our roots array. So forming the roots array will be like this. So our roots array is going to be just consisting of s3, s square, you now have s1, and you now have s to the 0. Is that okay? So for s3, we are going to choose 1, then we're now going to jump to the next term, which is what? 31 plus k. Then we're now going to jump, and on jumping we can't really find any place to stop, so maybe I'll just choose 0. So there's nowhere to jump to again. So if you want to find for s square, you start with this one over here, that's 7, and you now jump over to this term over here, and this term is a 25 minus 2k. So 25 minus 2k is the constant term in this case. So our task is to find our b1 and our c1 over here. So remember, when you have these last two terms, you just need to find only the b1 and the c1. So I'm just going to do for b1 over here. So to get b1, okay, you're going to reciprocate this guy, 1 over 7, and you now find the determinant of 7 1, then this and this, which is 25 minus 2k, and you now have 31 plus k Okay, so let's find the determinant. So b1 is now going to be 1 over 7, and into 7 times this gives me 7 brackets 31 plus k, and minus 1 times this gives me 25 minus 2k. Take note, there's a bracket here. Okay, so you have b1 is equal to 1 over 7, and into this times this is going to give you, if you calculate it very carefully, you're going to get 1, or rather a 2, 1, 7, and plus 7k, and you now have minus 25, then plus 2k. Okay, so when you open the brackets carefully, so our b1 will be 1 over 7 into 217 minus 25 should be 192, and plus 9k. So this is what we have for our b1. Our b1 is simply 192 plus 9k divided by 7. Okay, 192 plus 9k divided by 7. Then if you now want to solve for our c1, okay, sorry, I'm trying to conserve my space. So c1 is going to be, to get your c1, remember we've gotten our value for b1, and what we get as our value for b1? I got our value for b1 as 192 plus 9k divided by 7. So our c1 will fall in line, so we'll have, taking the reciprocal of this, you have 1 divided by 192 plus 9k divided by 7. Then you're now going to take this determinant formed by this and this, which is 192 plus 9k divided by 7. Then you have 7 over here. Then you need a term here, but since you can't get any term here, you replace it with 0. Then you now choose this one over here, which is 25 minus 2k. So at the end of the day, what we find ourselves doing is comparing this and this. So our c1 is going to be 1 all over 192 plus 9k divided by 7. And if you look carefully, you must have seen the answer. This times this is 25 minus 2k into 192 plus 9k divided by 7. Then this times this is minus 0, so we don't need it. At the end of the day, this one can cancel out this one, and you just be left with 25 minus 2k. So can you see that our last term over here, which is 25 minus 2k, this term is highly correspondent with what we have over here as the constant term, 25 minus 2k. So assuming we got that correctly, we have finished our root array. So our emphasis now is now going to be on the first column of the root array. So let's see what is happening in the first column. So I have a plus 1, a plus 7, and I now have two values that I don't know what their signs will be. But since these two are positive, now if I want my system to be stable, I have to make sure that I keep these two values also positive. Is that okay? So I have to make sure that I keep these two values also positive. So if I go ahead and interpret that, okay, and now see from the first column, of the roots table, for our system to be stable, we must ensure that these values and these values correspond in sign with what we already have here. In other words, they should be positive. So we should ensure that in the first case we have 192 plus 9k divided by 7 should be greater than 0. Okay, and we also have to ensure That's 25 minus 2k is greater than 0. So if we solve the two inequalities, starting with this one, we're going to get 192k plus 9k is greater than 0 times 7 is still 0. So I'll now have 9k is greater than, what do you now have? 0 minus 192. In other words, k is greater than negative 192 over 9. Is that okay? So k on one hand is greater than minus 192 over 9, and if we evaluate this, it gives us let me punch my calculator. It gives me it gives us negative 21.33, okay, on this side. So if we solve for this other hand, so we'll have 25 minus, on the other hand, we have 25 minus 2k is greater than 0. So if we solve, we'll have minus 2k is greater than minus 25. Is that okay? When you divide both sides by negative 2, you have k is less than, because a minus sign reverses the direction of your inequality. So you have k is less than 25 over 2, which is a 12.5. Is that okay? So you have what? K is less than 12.5. K is less than 12.5. Now let's match everything that we have together. So we're given from the onset, okay, we're given that k is greater than 0. Assume that k is greater than 0. So this value that we obtained at this particular point, k is greater than minus 21.33, k is greater than 0. So which one are you going to choose? You're going to definitely choose 0, because 0 is more positive than this one. So when you're choosing a greater symbol, you should choose the one that is like farther to the right. And at the same time, when I have something like k is less than minus 2, then k is less than minus 6. So which one will I choose? I'll choose this one than this one. So you always choose the one at the extreme point of your inequality. That's the more negative one or the more positive one. So between k is greater than minus 21.33 and k greater than 0, we are going to choose k is greater than 0. So we have k greater than 0 given to us. So in the second hand, we also saw that k is less than what? 12.5. So this has already formed like a block of values from 0 to 12.5. So you can put your values of stability. Therefore, for stability, our range of values for k in this interval, so we have 0 to 12.5. Okay, 0 to 12.5. So someone else might interpret this by actually saying k is such that we have 0 is less than k less than 12.5. So any value of k that actually falls within this particular range will actually make sure that our system is stable. In other words, it will make sure that we do not obtain roots whose real parts are positive. We are always going to obtain negative roots. So we're going to obtain negative roots. That means all the value of our s, all our s cube, the three roots of this characteristic equation. Remember, characteristic equation of degree n has n roots. So the three roots of this characteristic equation will always be negative as far as k is actually what? in this range between 0 and 12.5. So this is all about the roots stability criterion. I hope you learned a lot. I hope you can be able to reproduce if you find yourself dealing with any other example or any other problem. So don't forget to like this channel, and you can actually subscribe to this channel, because from time to time I'm going to be posting stuff relevant to engineering mathematics, relevant to control system engineering, and I believe you will find some of these tips useful. So once again, thank you for watching. For those of you who stayed to the end, I hope you actually learned a lot. Till the next video, stay blessed. Bye.